Hi, this is Vatya Vorparian with the Joys of Circuits Analysis, continuing on with Lecture 2. These lectures are based on my book, Fast Analytical Techniques in Electrical and Electronic Circuits, published by Cambridge University Press and available online by any bookseller. In this video, I'm going to talk about the determination of the poles of a transfer function and their physical interpretation. In the following video, I will talk about the determination of the zeros of a transfer function and their physical interpretation. In our last video, we said that a transfer function of a linear time invariant system can be represented with a block diagram as shown here. The transfer function is the ratio of the response to excitation in the transform domain with all initial conditions set to 0. And for a physical transfer function, it is best written as a constant G0 appearing up front, followed by a normalized polynomial in the numerator with leading term unity, and a normalized polynomial in the denominator with leading term unity. G0 is exactly of the same character as G of S, and the purpose of N of S over D of S is there to tell you how G of S behaves as a function of frequency. For example, over a certain frequency band, G of S could be going up or down, or going through some resonant peak or a notch, or staying flat. It's got to be one of those things. Now, D of S, we said, is called the characteristic equation of the system and is determined by the structure at rest. In other words, D of S has nothing to do with the applied excitation inside the structure, nor it has anything to do with the response anywhere inside that structure. We can illustrate these concepts on the block diagram as follows. First, since the response has nothing to do with D of S, we drop it out of the block diagram. And since we have to set ES equal to 0, we see that the whole block diagram reduces simply to a block with D of S written in it. So we ask ourselves the question, given a structure at rest, say one that has a bunch of resistors, capacitors, inductors, and possibly dependent sources, can we determine its poles or characteristic equation without having defined a transfer function on it? The answer is yes, of course. And the fastest way to do that for an nth order circuit is by the application of the n extra element theorem. We're going to learn that later. But the thing is that the idea behind an nth order circuit and a first order circuit is pretty much the same. So we are going to start with first order circuits and develop these basic ideas and then extend them to nth order circuits. Now, is there a mathematical basis behind all this? Of course. It is what you learned in your first differential equations class. You may or may not remember it, but you learned in that class for a constant coefficient linear differential equation, when you set the forcing function to 0, you know, the stuff on the right-hand side of the equal sign, you get the homogeneous equation, the one on the left-hand side of the equal sign. And it is the homogeneous equation set equal to 0 that gives you the characteristic equation or the eigenvalues of the system, or simply the poles of the system. Now, setting the forcing function to 0 is the same thing as setting the excitation of our linear time invariant structures to 0. And the homogeneous equation is the equation of the structure at rest. You do not have to worry about all that now, because we are going to learn how to do this for physical systems called electrical circuits. As promised, we are going to start with a first order circuit, shown here on the right is a capacitor C connected to a group of resistors R1 through R4, whose effective value is R1 plus the parallel combination of R3 with R2 plus R4. So effectively what we have is a capacitor connected in parallel with a resistor. And we know such a structure has a time constant given by the product of R and C. We write that time constant down as C times R1 plus R3 in parallel with R2 plus R4. We know the significance of this time constant in that it dictates the response of a parallel RC circuit to an arbitrary excitation applied to it. So we say the characteristic equation of the structure is given by 1 plus S tau, or 1 plus S over omega p, where omega p is the pole of the structure given by the reciprocal of the time constant. The time constant is the time domain picture of the structure. Its reciprocal, the pole, is the frequency domain picture of the structure. Now you will ask, how do you write d of s as 1 plus s tau? Well, the root of d of s is supposed to give me the pole of the structure, and the reciprocal of the pole of the structure is the root. So effectively, the root of d of s gives me the time constant of the structure. Conversely, working it backwards, if I know the time constant of the structure, then I know the root of the polynomial d of s, and hence I know the polynomial itself. It's as simple as that. When we set d of s equal to 0, the root of it is the pole minus omega p, and the reciprocal of the pole is the time constant. This is a left half-plane pole shown in the sigma j omega plane. So this is it. There's nothing more to it. You know the time constant, its reciprocal is the pole, and hence you know what d of s is, because you know its root. Now you're thinking, what if there were a whole bunch of other capacitors? Well, then you're asking about the n extra element theorem. And I can tell you from now, it is nothing more than a generalization of what you just saw. If there are more reactive elements, each reactive element will have an accompanying time constant associated with it, which we are going to talk about how we determine it. And then these reactive elements come in pairs, then in triplets, then in pairs of fours, depending on what the order of the system is. And all you need to know is the permutation rule of how these things come in pairs. But in each and every case, all you're doing is you're determining a bunch of time constants. But that's getting ahead of us. Right now, let us just concentrate on the basic idea that we determined the time constant of a first-order structure simply by looking at it, because we're so familiar with it, and we said that the characteristic equation is 1 plus s tau. Because when I set the characteristic equation to 0, its root gives me the pole of the structure, or simply the time constant of the structure, which is the reciprocal of the pole. Now you see that I have drawn this circuit as a bridge, but really it is nothing more than 3 different branches in parallel. But the reason I drew it as a bridge is because in the following example I'm going to be excited in different ways, and one of them will give us a bridge connection. Now, since there are 3 branches, we can excite this circuit in 3 different ways by inserting a voltage source inside any one of the 3 different branches. Also, we can excite this circuit in 6 different ways by connecting a current source across any of the 4 nodes. Hence, we have a total of 9 different ways of exciting this circuit in a manner whereby when we set the excitation to 0, we get back the same structure. That means that there are other ways of exciting this circuit, such as applying a voltage source directly across an impedance branch. But that will change the structure. I'm not interested in it at this point. There's nothing wrong with that. It's just that I'm not interested in it right now. I want to talk about these 9 different ways of exciting this circuit in a manner that when I set that excitation to 0, I always get back the original structure. Along with each one of those 9 different excitations, I can have different transfer functions associated with each. For each excitation, I could be studying the current in any one of the branches or the voltage across any one of the elements here. And I have all kinds of transfer functions that I'll be determining that way. And the thing is that all of those transfer functions will have the same denominator, because once you set the excitations of those transfer functions to 0, you always get back the same structure, and hence they all have the same denominator, 1 plus s tau, where tau is the time constant that we determined previously. To reiterate then, we are able to speak of the pole of a system without having to define a specific transfer function on it. No surprise here, because the pole is the characteristic value of the homogeneous no-forcing function, that is to say, first-order constant coefficient differential equation. We get the denominator d of s, whose root is the time constant, or the pole of the system, and its reciprocal is the time constant of the structure. And now we are going to excite the bridge with a current source Is and study the voltage Vs across it. And here's the current source being applied to this circuit, and here's the voltage appearing directly across it. And we want to study the ratio of Vs over I of s, which is equivalent to saying that we're trying to determine the impedance looking into this port of the network, or the driving point impedance at this port of the network. This is the transfer function we are interested in. And like any other transfer function discussed earlier, this input impedance has the form R0 followed by n of s over d of s, where R0 is a constant of the same character as the n of s, and in this case it is really the low frequency asymptote of the input impedance, where the capacitor is an open circuit. So for this impedance function, we know what d of s is. It is 1 plus s tau, where tau is the time constant determined earlier. And the reason is that the excitation function of this impedance function or transfer function is a current source connected at this point here, which when we set equal to 0 becomes an open circuit, and we get the structure that we talked about earlier, whose time constant is R1 plus R3 in parallel with R2 plus R4 times C. Now it's a good time to show the connection between d of s that we have been studying for this structure and the trick of the extra element theorem that I showed you back in lecture 1 when determining the input reactance of this bridge circuit. At that time I showed you how the extra element theorem can help you find that input reactance by first taking out the capacitor and determining the input resistance. That gives you R0, which is the input impedance at low frequencies where the capacitor is an open circuit. We called R0, if you remember, the partial credit answer. And then I showed you how the capacitor can be reinstated back in the expression of the input impedance using the modification factor following R0. For that, you needed to perform 2 additional calculations. One in the denominator, and that is the one that I'm interested in right now, and another in the numerator, which is reserved for the next lecture. In the denominator, what you had to do was open the input port like that and look back into the circuit where the extra element was connected and determine the resistance seen by that extra element. This is nothing more than computing the time constant of the structure that we've been doing all along, with the excitation removed. And that yields the d of s of the structure. So you see now, when I said at the time, and for the denominator calculation, look back into the port where the extra element was connected with the input port open, that meant really look back into the network with the excitation of this impedance function set equal to 0, which is the current source connected at that port. Now you see the connection between the two. And this is how we're going to build up to the extra element theorem, example by example, part by part. We are now going to excite the same structure by applying a current source across a different branch of the circuit, in this case across R2, and determine the current gain I3 to I1 of S, where I3 is the current flowing through R3. This transfer function is expected to have the same form as all the others, a constant appearing up front, followed by the same denominator that we have determined so far, because when we set the excitation equal to 0, we recover our original circuit. And then we have a numerator n of s, which we're going to be determining in our next lecture. AI0 is the current gain at 0 frequencies when s equals to 0. And that corresponds when the capacitor is in open, which is easy to determine. And we'll do that in the next slide. So we now determine the low frequency asymptote by taking the capacitor out of the circuit. That leaves us with a very simple current division between R2 and R3 plus R4. That gives us the constant AI0. And the transfer function can now be written as AI0 n of s over d of s, where AI0 has been determined and d of s has been determined. N of s will be determined in the next video. The last example in this video that I would like to consider is that of the common emitter amplifier with an emitter bypass capacitor. We will determine its voltage transfer function V out over V in of S using the equivalent circuit model of the transistor shown here. This is a first order system, so we expect the voltage gain to be of the form A0 into 1 plus S over omega Z divided by 1 plus S over omega P. First, we are going to determine the denominator d of s, or the pole of the structure. And afterwards, we are going to determine A0, which is the low frequency asymptote of the voltage gain, where the capacitor is an open circuit. We are now going to determine d of s of the voltage transfer function, which means we are going to set its excitation equal to 0. Its excitation is V in of s, so we set that equal to 0 and obtain the following structure. In this structure, we see that CE is effectively connected in parallel with the resistance looking back into the circuit from the emitter port. Now, this is a first order system, so d of s for this circuit is going to be simply 1 plus S tau E, where tau E is the emitter capacitor multiplied by the effective resistance looking back into the circuit from the emitter port. We can simplify this by recognizing that RE, R super E rather, looking back, is the parallel combination of the emitter resistor itself with whatever follows looking back into the emitter port after it. So we can keep the emitter resistance RE out of the picture at first and just determine R super little e, which is the impedance looking back into the circuit from the emitter port after the emitter resistor RE. And we'll do that in the next slide. Now R super little e is determined by following these simple steps. we connect a test current source at the emitter port as shown, and we determine the voltage Vt that appears across it between the emitter port and the ground. Vt appears across Rs plus R pi. Therefore, we can write Vt is equal to minus Ib into Rs plus R pi. We also know that the test current is the sum of the base current and the collector current, so that It equals to minus Ib into 1 plus beta. Dividing the two, Vt over It, yields R super little e, and that is Rs plus R pi divided by 1 plus beta. This is a well-known result of the common emitter amplifier. It is the reflection of the resistance in the base circuit into the emitter circuit, or simply the buffer action of an emitter follower. Hence, R super capital E, which is the effective resistance seen by the capacitor in the emitter, is given by the parallel combination of the emitter resistor and R super little e. And therefore, the denominator is given by 1 plus SCE R super E, or 1 plus S over omega p, in which omega p is the reciprocal of the time constant, given by a CE and parallel combination of RE with RS plus R pi divided 1 plus beta. And now we determine A0, the low frequency or DC voltage gain of the amplifier, by opening the capacitor. There it goes. And now we can write the following simple equations. First, we say that V in is the voltage drop across Rs plus R pi, which is Ib into Rs plus R pi, plus the voltage drop across Re, which is the sum of the base and collector currents flowing through Re, Ib into 1 plus beta Re. The second equation is the output voltage is given by minus beta Ib times Rc. The ratio of these two yields the inverting gain of the common emitter amplifier with an emitter resistor, a very familiar expression that I am sure you've learned in your first electronics class. To summarize then, the voltage transfer function of the common emitter amplifier with an emitter capacitor is given by A0 into 1 plus S over omega z divided by 1 plus S over omega p, in which A0 and omega p are given as follows, and in the next video we are going to determine omega z, which is the numerator of this transfer function.